The history of industrial catastrophe contains few events that altered the global consciousness as profoundly as the Chernobyl disaster. It was not merely an accident. It was the ultimate, systemic blunder of Soviet-era engineering and centralized governance. On April 26, 1986, the catastrophic failure of Reactor Unit 4 at the Chernobyl nuclear power plant in the Ukrainian Soviet Socialist Republic released enough radiation to contaminate millions of square kilometers, instantly vaporizing the surrounding area and ushering in a decades-long political and environmental crisis. This disaster, the result of a flawed reactor design combined with a reckless safety test and a culture of secrecy, was a physical, undeniable manifestation of the Soviet system's terminal sickness. The immediate cost was human life and environmental poisoning, but the subsequent, ongoing financial cost would run into the tens of billions of dollars, becoming a burden borne by the entire global community. The immediate aftermath was defined by heroic, desperate damage control, executed by soldiers, firefighters, and engineers, the liquidators, who faced certain exposure to lethal radiation. Their first and most critical engineering task was to contain the molten core, which was burning with the intensity of 1,000 suns and threatening to melt through the reactor foundation and contaminate the groundwater that fed the entire region. Helicopters dropped thousands of tons of sand, clay, lead, and boron directly onto the exposed reactor core. This act, though crude and necessary, was not a solution. It was a desperate attempt to stabilize an actively erupting volcano of radioactive materials, a stopgap measure that bought the world precious time at an unforgivable human price. Following this initial stabilization, the Soviet state rushed into the first major engineering blunder of the cleanup: the construction of the sarcophagus, officially known as the shelter structure. This was a colossal engineering feat born out of pure urgency, built under almost unimaginable radioactive conditions. The goal was to construct a massive, reinforced concrete shell around the wrecked reactor building in a mere 206 days. The structure was erected by workers who could only spend minutes at a time near the reactor, utilizing heavy remotely controlled machinery where possible. Every segment of the sarcophagus, from the foundation to the final closure, was a direct compromise between structural integrity and the need to protect human life from the lethal radiation fields. The sarcophagus was an achievement, but it was fundamentally flawed from the moment it was completed in late 1986. Due to the haste of its construction, the lack of proper foundation preparation, and the inability to thoroughly inspect joins in the high radiation zones, the structure was structurally unsound. It was riddled with cracks and penetrations, large enough for external moisture to enter and radioactive dust to escape. Furthermore, the massive explosion had left the structure resting precariously on the damaged remains of the reactor building itself, with a vast concrete roof relying on unstable walls and beams. It was never intended to be a permanent solution, but a temporary containment measure with an expected lifespan of barely 20 to 30 years, designed only to buy the scientists time to devise a truly lasting solution. Inside this hastily constructed concrete tomb lay the most dangerous concentration of radioactive material on Earth. The molten nuclear fuel, mixed with concrete, sand, and metal, had cooled and solidified into strange lava-like formations known as fuel-containing materials, FCMs, the most infamous of which is the solid mass known as the elephant's foot. These FCMs, containing over 200 tons of uranium and fission products, posed a persistent double threat. First, they were dangerously radioactive, emitting lethal doses that made access impossible. Second, the structural integrity of the sarcophagus meant that water leaks could lead to highly corrosive conditions and, critically, raise the risk of a secondary, steam-driven nuclear explosion if water were to pool around the fuel. The core problem facing the Soviet and, later, the Ukrainian government was the instability of the sarcophagus's roof, an engineering nightmare known as the mammoth beam. This massive concrete and steel beam, supporting the original reactor hall roof, was severely damaged but was still holding up the compromised sarcophagus structure. The fear was that the slightest seismic activity, a severe storm, or simply the continued deterioration of the concrete over time would cause the beam to fail, leading to a catastrophic collapse of the entire sarcophagus. Such a collapse would release a massive plume of radioactive dust, aerosols, and fine debris high into the atmosphere, repeating the environmental contamination of 1986 and spreading the disaster far beyond the exclusion zone. The international community was fully aware that the $1 billion sarcophagus was a ticking time bomb. The catastrophic potential of its failure demanded a collaborative, global response. By the late 1990s, an international consortium, spearheaded by the European Bank for Reconstruction and Development, EBRD, and supported by contributions from dozens of countries, was formed. Their mandate was clear: design, fund, and build a second permanent containment structure, a giant engineered shield that would render the original sarcophagus irrelevant and finally secure the site for the next century. This was the birth of the new Safe Confinement (NSC) project, a necessity born entirely out of the failure of the original, rushed Soviet response. The new Safe Confinement was perhaps the most ambitious, complex, and expensive environmental engineering project ever conceived. It was designed to be an entirely self-sufficient, movable structure large enough to enclose the entire sarcophagus and the crippled Reactor Unit 4 building. The structure needed to withstand extreme temperatures, seismic events, and, crucially, possess a 100-year operational life with minimal maintenance. Its primary function was threefold: to prevent the collapse of the aging sarcophagus, to contain the radiological material within, and to allow for future, safer deconstruction of the unstable sarcophagus and the removal of the nuclear fuel. This was an engineering solution to a political problem, necessitating unprecedented levels of global cooperation and funding. The technological requirements were phenomenal. The NSC had to be constructed away from the high radiation zone and then slid into place over the reactor building, a delicate process requiring massive, custom-built jacking systems. The structure itself was designed as a colossal arch, made of steel, not concrete, to provide greater structural flexibility and stability. It would weigh over 36,000 tons and stand taller than the Statue of Liberty, making it the largest movable land structure ever built. Every design decision, from the choice of specialized corrosion-resistant steel to the integration of remotely operated cranes and ventilation systems, was dictated by the failure of the sarcophagus and the fundamental reality that human presence inside the new structure would be impossible. The NSC was, in essence, the ultimate piece of remote-controlled, over-engineered containment. The initial cost estimates for the new Safe Confinement were already immense, but they quickly began to spiral upwards as the project faced unprecedented engineering challenges and bureaucratic hurdles across the 2000s and 2010s. The final construction cost would ultimately exceed $2.5 billion USD, a figure that does not include the ongoing operational costs, the aid provided to Ukraine, or the billions spent on the initial cleanup. This escalating expenditure became a symbol of the true, hidden cost of the 1986 Soviet blunder, a debt that was transferred from a closed political system to the global community, transforming a single nuclear accident into an international, century-long financial commitment. The construction of the Ark began, marking the start of a new, complex chapter in Chernobyl's costly history. The construction of the new Safe Confinement was a massive challenge that required the creation of an entirely new, temporary industrial complex near the Chernobyl site. The design demanded the structure be built approximately 327 meters, or 1,073 feet, away from the radioactive Reactor 4. This distance was a critical safety buffer, allowing thousands of workers to assemble the massive steel structure without being exposed to lethal doses of gamma radiation. This necessity meant that the team had to design a structure that was not only gargantuan and complex but also fundamentally movable, leading to years of complex foundation and specialized component manufacturing before the first arc segment could even be lifted. The scale of the NSC was bewildering, often compared to landmarks like the Statue of Liberty or the Eiffel Tower in terms of sheer volume and weight. The structure is 108 meters, 354 feet, high, 257 meters, 843 feet, wide, and spans 162 meters, 531 feet, long. It required over 36,000 tons of specialized steel, designed to withstand the corrosion typical of the highly humid, contaminated atmosphere. The complex framework was erected in two halves, or arches, using custom-built cranes, a process that was meticulously executed section by section. This modular approach was vital. Every connection and every weld had to be perfect because, once installed, most parts of the structure would be virtually inaccessible for routine maintenance due to the high residual radiation levels inside the arch. A significant engineering challenge arose from the highly specialized ventilation system, which was integral to the NSC's function. The confinement was designed to operate under negative pressure. This essential feature ensures that any contaminated air inside the structure, where the decaying sarcophagus resides, is pulled inward and passed through high-efficiency particulate air (HEPA) filters before being released. This prevents the escape of radioactive particles into the environment, securing the external perimeter. Designing a sealed envelope of this enormous size, capable of maintaining consistent negative pressure in a highly corrosive environment for over a century, required cutting-edge technology and materials that accounted for every possible failure point. The financial management of the project itself became a persistent administrative blunder. The cost, initially estimated in the hundreds of millions, ballooned to over $2.5 billion. This escalation was driven by several factors: the extraordinary safety standards required, the continuous need to adjust designs based on new data about the deteriorating sarcophagus, and the inevitable political and bureaucratic hurdles of managing contributions from dozens of different international donor nations. Each new challenge meant a fresh round of funding requests and negotiations, ensuring the project remained in a state of financial crisis throughout much of its construction timeline, often delaying critical phases. The structural integrity of the NSC was paramount, particularly its reliance on the colossal jacking system required to move it. The entire arch had to rest on two massive concrete foundation beams constructed adjacent to the assembly site. The system was designed to use 116 special hydraulic jacks, applying controlled pressure to lift and slowly push the 36,000-ton structure. This was not a simple movement. It was a slow-motion, delicate slide that required the continuous, precise synchronization of every jack, managed by complex computer systems to prevent the slightest misalignment, which could have led to a catastrophic structural failure of the arch itself. And so, the moment of truth arrived in November 2016. After nearly a decade of complex construction, the massive arch was finally ready to be moved into position. This process, known as skidding or sliding, was a spectacle of modern engineering mastery, broadcast globally as the definitive act of securing the 1986 disaster. The structure was moved over a distance of 327 meters, 1,073 feet, an event that took 5 nerve-wracking days. The sheer size and mass meant the movement was glacial, proceeding at a rate of only a few meters per hour. The world held its breath, knowing that this was the final, irreversible step. The slide presented its own unique set of immediate environmental and safety risks. As the NSC approached the dilapidated sarcophagus, the radiation field intensity dramatically increased. The project engineers had to account for the possibility that the movement itself could disturb the fragile, unstable structure of the sarcophagus, potentially triggering a localized collapse or releasing a plume of dust. Specialized monitoring equipment measured seismic vibrations and particulate release in real time, ensuring that if the movement caused the sarcophagus to shift, the sliding operation could be stopped instantly, minimizing any potential secondary release. Successfully completing the slide and mating the NSC to its final foundation near Reactor 4 was only the beginning of the end. Once the arch was secured, the real work of decommissioning could begin under the cover of the new shield. The NSC is equipped with enormous remotely operated crane systems and manipulation technology, allowing engineers to begin the extremely dangerous process of stabilizing and dismantling the original sarcophagus without risking human life. This technological infrastructure allows technicians to cut, lift, and remove the unstable steel and concrete elements from inside the confinement, gradually neutralizing the threat posed by the original flawed structure. The ultimate goal of the NSC is to facilitate the complete removal of the nuclear fuel, the highly radioactive FCMs, from the wrecked reactor. This is the final, most dangerous, and most expensive phase of the decommissioning process. The NSC's durable, controlled environment provides the necessary containment envelope to develop and deploy specialized robotic systems capable of locating, cutting, and packaging the elephant's foot and other fuel masses. This task is projected to take decades and will require continuous international funding and technological innovation, proving that the true long-term cost of the 1986 blunder far exceeds the $2.5 billion spent on the arch itself. The successful completion and installation of the new Safe Confinement was hailed as a monumental victory for global cooperation and engineering. It was a powerful, tangible message that humanity could, through collective will and technological brilliance, contain its most catastrophic errors. However, the NSC remains a silent, constant reminder of the failure that necessitated its existence. It is a $2.5 billion band-aid covering an ongoing wound, a physical monument to the fact that the cost of cleanup, maintenance, and eventual fuel removal will continue to burden Ukraine and the international community for the next century. The immediate physical threat was contained, but the financial and political legacy of the Soviet blunder will endure for centuries to come. The installation of the new safe confinement did not mark the end of Chernobyl's financial burden. It merely transitioned the expenditure from construction costs to long-term operational costs. The NSC, being the largest movable land structure ever built, is a complex machine in itself, requiring continuous ventilation, environmental monitoring, and meticulous maintenance to ensure its 100-year lifespan. This operational budget, which runs into the tens of millions of dollars annually, must be permanently guaranteed by the international community and Ukraine. The long-term costs of simply managing a containment failure, therefore, dwarf the initial construction cost, turning the billion arc into a century-long, multi-billion-dollar annuity of financial obligation. One of the most complex and persistent threats is the issue of water infiltration within the original sarcophagus. Despite the tight seal provided by the NSC, preventing water from reaching the highly radioactive fuel-containing materials, FCMs, remains a critical challenge. Water accelerates corrosion, potentially compromising the structural remnants of the reactor, and creates the risk of initiating self-sustaining fission reactions if it pools around the fuel masses. Engineers and robotic teams must continuously monitor humidity and temperature, using remotely operated systems to seal cracks and pump out any accumulating water, a perpetual battle against entropy dictated by the hasty and imperfect construction of the 1986 sarcophagus. Beyond the NSC, the surrounding exclusion zone itself represents a permanent financial and environmental liability. This massive, contaminated area, a radius of 30 kilometers, must be continuously monitored, policed, and managed. It requires vast resources for forestry management, fire suppression, to prevent the spread of contaminated ash, and the maintenance of complex security fences. While it has become an unintentional wildlife refuge, its management is dictated by radiological contamination, necessitating an unending budget for security and environmental maintenance, ensuring that the 1986 blunder continues to consume state resources decades after the fact. The ultimate goal remains the safe removal of the fuel-containing materials, FCMs, a monumental task that embodies the final, enduring engineering challenge. These solidified lava masses are highly abrasive, lethally radioactive, and difficult to manipulate. The NSC provides the shelter, but the technology for removing the estimated 200 tons of fuel safely is still under intense development. This requires creating entirely new methods of robotic mining and remote handling, procedures that carry massive cost implications and may span another 50 to 70 years, pushing the final, total cost of containing the Chernobyl disaster well into the mid-22nd century. The financial pressure on Ukraine is immense. Although international donors provided the capital for the NSC's construction, the long-term operational costs and the eventual decommissioning of the original reactors place a significant strain on the national budget. The Chernobyl legacy functions as a geopolitical anchor, consuming funds that could be allocated to infrastructure, education, or defense. This dependency on international funding for managing a domestic environmental disaster highlights how the 1986 Soviet blunder morphed into a permanent, multi-generational vulnerability for the sovereign nation of Ukraine. The psychological and public relations cost of the NSC is also significant. While the arch is hailed as an engineering triumph, it remains a symbol of vulnerability. It serves as a constant, tangible reminder that even the most technologically advanced nations can suffer catastrophic failures with multi-century consequences. The very existence of the $2.5 billion arc perpetuates global anxieties about nuclear power, fueling public resistance to new reactor construction worldwide, regardless of advancements in modern safety protocols. The original blunder continues to cast a long, chilling shadow over the energy policies of nations far removed from Ukraine. The international cooperation that funded the NSC, while praiseworthy, also reveals a fundamental political failure. The NSC was paid for by the global community, effectively transferring the financial burden of the Soviet failure, a failure born of secrecy, flawed design, and governmental negligence, to the world's taxpayers. This established a dangerous precedent, that a state, through catastrophic negligence, can externalize the costs of its internal engineering blunders onto the global financial system, raising questions about accountability and responsibility in future large-scale technological failures. As the NSC settles into its long-term role, political attention tends to drift elsewhere, creating the persistent risk of funding fatigue. The massive initial emergency is over, but the dangerous long tail of the disaster remains. Maintaining the necessary political focus and securing consistent funding over a 100-year horizon is perhaps the greatest non-technical challenge. The risk is that future generations, detached from the trauma of 1986, will fail to prioritize the multi-million-dollar annual budget required to maintain the NSC, allowing the structure to gradually deteriorate and recreating the very threat it was built to contain. The ultimate purpose of the NSC is to make the highly contaminated site safe enough for its final disposition, which includes dismantling the original reactor for and safely disposing of the 200 tons of nuclear fuel. The project's success will ultimately be measured not by the successful sliding of the arch, but by the safe conclusion of this decades-long decommissioning phase. Until then, the NSC is not a solution, but an immensely expensive pause button on a nuclear crisis, a monument to the fact that when engineering fails at this scale, the recovery is measured not in years or decades, but in centuries. As we reach our conclusion, it is clear that the Chernobyl new safe confinement is the definitive case study in the ultimate cost of a technological blunder hidden by governmental secrecy. The $2.5 billion arc, the $17 billion estimated total cleanup, and the centennial operational costs all represent the true, unvarnished price of prioritizing political expediency and flawed design over scientific rigor and human safety. The cost of a nuclear disaster is perpetual, and the NSC stands as the world's most costly and technologically complex insurance policy, reminding us that some blunders are so profound that their debt becomes the permanent inheritance of future generations. Please like and subscribe if you enjoyed this narrated documentary. Until next time, thank you for exploring billion-dollar blunders with us.